means we shall use the thyristor. We shall use the thyristors here. So I have given you the idea of the thyristors, right? How it is turned on, how it is turned off. Did I give you the idea?
Yes, sir.
Okay. Now, so in the AC to DC converter, this is also rectified, but we will use the thyristor over there of the SCR. And here we shall use only the diodes. So mainly these are the two things I like to cover, but it is not that easy. It has a lot of topics to cover. Okay, so let us go little details. Okay, so go to the. Let me take my glass. Sorry. Okay, so now, so what do we want to do? Let us give you the simple diode circuits. Are you familiar with these diode circuits? Are you familiar?
Yes, sir.
Have you seen these diode circuits before? What type of circuit this is? We have learned this one in our well, in the second semester. We have learned this one. So what
Rectifier
type of
circuit?
rectifier circuit? But there are two types of rectifiers, right?
Yes, sir. Half wave and full wave.
No. Like according to the number of diodes. So two diodes are here. This is known as the center tap. Can you remember this? Center tap diode rectifiers. Center tap transformer actually. Transformer based diode rectifier. This one is the bridge rectifier. Can we remember this one? No. So here what we do. So I believe that you are familiar with the term transformer here. The transformer is an electrical device that transfers the energy from primary side to secondary side. This is the primary side, and this is known as the secondary side, right? Of your locality over a pole, they carry this transformer. Actually, high voltage is applied here, and you can step up or step down. You can step up or step down the voltage by using the transformer. Here, what we may use the turn ratio could be 1:1. If the turn ratio of the primary and the secondary I am asking you.
Sir, your voice is cutting.
Just a moment. It's just cutting back. Hold on. So you're not listening to me, right?
স্যার এখন শোনা যাচ্ছে।
শোনা যাচ্ছে? এখন
জি
কি
স্যার।
কেটে কেটে যাচ্ছে?
না স্যার এখন ঠিক আছে স্যার।
ঠিক আছে? Okay.
জি স্যার।
So now look here, because I have changed the Wi-Fi from it was to the another one. Today connected to the LAN. Okay, LAN is better. Okay,
স্যার
let us
ল্যান বলতে
see.
কি স্যার ইথারনেট কানেক্ট করতে চাচ্ছেন? ইথারনেট কেবলটা?
হ্যাঁ।
জি স্যার এটা বেটার হয় যদি স্যার বাসার অন্য কেউ ইউজ না করে এই মুহূর্তে।
জানি না, আমি ওয়াইফাই আছে। আচ্ছা, যদি সমস্যা আমাকে বলো, হ্যাঁ?
আচ্ছা স্যার।
Okay, so now look at the transformer. If the turn ratio of the primary and the secondary is same, like N1 by N2 equal to say 1. Hello,
ইয়েস স্যার।
are you listening?
ইয়েস স্যার।
So I asked you a question. You have applied a voltage from A to B here. Here to here. I have applied a voltage here to here. This voltage is 230 volt. If turn ratio is 1:1, what will be voltage between C to D?
সেম ভোল্টেজ স্যার 230।
230 volt. Okay, now what we did in the secondary winding, so someone must unmute your mic and you have to interact with me. Otherwise, how can I know my voice is going to you? Okay? Okay? Okay, so now
Yes,
the voltage, yes, same voltage 230, but in the middle of the winding, in the center of the secondary winding, suppose this is your primary winding, this is your secondary winding, we take a tapping here. This is known as the center tap. So this is your say half, and this is also half, and suppose this is 1. So then what will be the voltage? If this is your 230 volt, what will be the voltage from here to here?
230 by 2 in each.
Yes, that means 115 volt, right? It will be 115 volt. So voltage will be divided. Then you will have to work with this voltage. The peak value of this voltage will be there. Okay. If 115 volt is the RMS value, then what will be the peak this VM? Can anyone tell me? What is this one? What is this one actually?
It will be the RMS multiplied by √2.
Right, RMS multiplied. So 115 multiplied by √2. That will be your VM here. So you will get that this VM and also this one. This is the one. If we know the VM, do you know what will be the average value for the full wave rectifier?
We will have to divide it by pi.
Yes, so VBC or V0, DC value or V average, that will be your 2 VM by pi. 2 VM by pi. This is for the full wave rectifier. For the half wave rectifier, it will be VM by pi.
Yes.
So this will be your say 0.636 probably VM as far as I remember. But if you put if you replace this VM by VS, then what will happen? So your VDC will be say 2 VM by pi. So VM can be replaced by √2 VS. √2 VS. And if you calculate then this one, then you will get 0.09 VS. Okay? What is this VS? Hello, you have to sometimes say
yes
sir, yes sir, no sir. So this is 0.9 VS. So what is VS?
Source voltage.
RMS value of the source voltage. RMS value of the voltage between this point to this point.
Oh,
This
sorry,
is your
sorry. Is it like secondary side?
right? This is the secondary side. I'm talking about the secondary side. Okay, these are the things actually we have already covered earlier, and but when we go back and see for the bridge rectifier, we'll come back again. So this is the another one, DC to DC converter. DC to DC converter is also known as chopper, right? Chopper or voltage regulator circuit. Chopper, look here, it is known as chopper. So your Faima should have started this one. Did he start?
Yes, sir.
Chopper?
Sir, Faima sir mentioned the buck converter and boost converter so far.
Yes, this is the buck converter, the figure of the buck converter. If you look at the figure, so this is the DC voltage, and there is a switch here. This switch is the IGBT. I will come back for this IGBT. IGBT is the insulated gate bipolar transistor. So the gate will be insulated. It will be like your MOSFET. Okay. So this will be when you will get, it will get the pulse like this. GE means that this is the voltage. This is the voltage between this and this. This is your G point and this is your E point. When it will get a pulse like this, then only this switch will be turned on. Then this voltage will be, this diode will be reverse biased, and this voltage will be V0 will be VS. That we got here. Okay. And this is your on time. T1 will be your on time. And then when it will be open, the current should flow through this diode, and if this diode is conducting, that the voltage, this is short circuit, the voltage will be 0. So you will get a voltage like this. And this is the chopped, this is the chopped voltage, and finally you will get that the output with average value of this output voltage will be like this, and this V0 will be delta Vs. Delta is nothing but the in your book, this is K, this is your duty cycle. So did he cover up to that?
Yes, sir.
Duty cycle K, that is your T on by T. T is nothing but the total time period. Okay, T1 yes, here, T1. So with this one, if you change T1, look here, if you change this one, T1, if you change this one like this one now, so your T1 is increased and your duty cycle will be increased, and your output voltage V0, the DC voltage will be increased. So we will cover all these things elaborately. I don't want to talk about much about this one right now. And this is your inverter. DC to AC converter is nothing but the inverter. And this inverter will be your square voltage type inverter. Sometimes people call it quasi type inverter. It is not exactly sinusoidal, rather than the output voltage will be this one. It is alternating but not sinusoidal. So what happened? This switch and this switch will be turned on for the positive half cycle, and then this voltage, the current will go this way. This will be open. So okay, okay. So this will go okay. This will go this way, this way, this way. The current will go this way, and then this way, and this way it will come back this way. So if you apply the voltage, Kirchhoff voltage, you will get a positive voltage here. And if you since the current is going there, positive to negative, so this V0 you will get that this V0 will be positive Vs. And for the negative half cycle, this one and M3 and M4 will be turned on, and then we will get that negative voltage. This way we can always get the operation of the inverter. So your time habits are, inshallah, will cover this one, and we will have the good knowledge. So AC to DC converter we have already. Okay, this is the what is the device we have used here? Is it diode? Is it diode?
No, sir. Thyristor.
Thyristor. So the condition to turn on this thyristor is that it must be forward biased. Only 33 students are present. If the thyristor is forward biased, the thyristor is forward biased by this voltage, but it will not conduct just as a diode, because unless you apply the gate pulse, you have to apply a gate pulse here, then only it will be conducting. The current will flow here. Did I say this one? Did I say
sir.
that thing in the previous classes, or do you want me to repeat it?
Sir, can you repeat it, sir?
Okay. The characteristics of this thyristor is that, suppose very simple circuit here. Suppose this is your resistor. Suppose you have applied a positive. Okay. So, what is the biasing condition of this thyristor? What is the biasing condition of this thyristor right now? Tell me something.
So right now it is
This
reverse
positive
bias.
is here. How? This positive is here. So it is forward bias, right?
Yes, sir.
So now, suppose after a time of, say, T1, you have applied a gate pulse. We call it IC. Here, this is your gate, and this is your anode, and this is your cathode. So you applied a gate pulse. Unless you applied any gate pulse, this thyristor will not be conducting. Okay. So that means it will be turn off this one. So if this is your V0. So what will be the voltage if the diode is off, that is open? Is there any current going through your resistor?
No, sir.
So there will be no voltage, right? You will get a 0 voltage. And when you have applied a pulse here to turn on the thyristor, the condition is that it must be forward biased and you must give a firing pulse. Okay. So you have applied a firing pulse here. If it is omega t, we can say, okay, at omega t equal to alpha, we have applied a firing pulse. And then only the thyristor will be conducting. If it works as an ideal switch, what will be the voltage V0?
VS.
Yes. So from here you will get this one. So if it goes like this, and if you apply any pulse, nothing will work. It will be conducting forever. So how to turn off the thyristor then? Either you have to reverse the voltage, or you have to withdraw the source voltage. Then only the current will stop. Otherwise, it will not be turned off. It will be conducting for here. Suppose your VS is open. So then only the current will be 0. So look here, this is your input voltage you have applied. So this is the forward voltage for this thyristor, and we have applied the gate pulse here. Gate pulse has been applied here. So then the output voltage will be, let me use the pen. The output voltage will be this one. Then the thyristor, since the voltage is 0, and also the current, this is the resistive load, and current must be also equal to 0. So to turn off the thyristor, the voltage across it must be 0 or reversed or no, nothing. And the current through it must be 0, then this thyristor will be turned off. And then when it goes to the negative cycle, up cycle, so this thyristor will be forward biased like this. And you have applied a voltage, what is the gate current here, IZ2, that has been given here pi plus alpha. So the output voltage will be like this. So if I plot this one, your output voltage will be alpha by pi, and then this is pi plus alpha, and it will, what will be this one? What will be this angle?
So
what will
2
be
pi.
this angle? 2 pi. So then you have to find out the average value. Since it is repeating, if you have to integrate from alpha to pi and divided by pi, then you will get the average value. You can get you can do that. We will do that thing later, inshallah. Okay?
Sir.
Yes.
Sir, then if we want a pure sinusoidal output, then we will have to tune the gate pulse timing according to the supply frequency, right, sir?
Yes. So you have to this gate pulse must be synchronized with the supply voltage. You are correct. You must know the where you are. If you apply the gate pulse here, you are giving the gate pulse here. Suppose you are giving the apply the gate pulse here, then what will happen? You are applying, suppose this is your IZ1 and you are applying another gate pulse here, IZ2. Then what will happen? What will be the wave shape of your output voltage? You are turning, you are giving the gate pulse at omega t equal to 0. Then what will be your wave shape of the output voltage?
Sir, the figure in the, I mean, the figure given below, sir.
That means the whole things, right?
Yes, sir.
Because you have turned it on and you have already turned it on. So you will get the same as the diode rectifier, right?
Yes, sir.
Now, if you are delaying, this is also called delay angle. You are delaying and sometime maybe omega t, this is pi. So, okay, alpha may be equal to say 45 degree. Then after 45 degree, you have applied the gate pulse here. So you will not get any voltage here. And then you will get the voltage like this. You got my point?
Yes, sir.
Then you are applying the another gate pulse here to gate pulse to where? To which thyristors? Suppose we want to give the gate pulse here. So this gate pulse will be applied where? Can anyone tell me this gate pulse will be applied where? T1 or T2?
Sir, can you please repeat the question again? I missed it, sir.
My question is that, okay, for the this positive voltage makes this diode forward bias, and we have applied the gate pulse at omega t equal to alpha, then we will not get any voltage until alpha. Then at omega t equal to alpha, this thyristor is turned off, short circuit. Then you will say that this V0 will be your simply Vs. So we will get this one, and this voltage is going to 0. And also, since this is resistive load, the current is 0. To turn up the thyristor, the condition is that it must be 0 voltage or 0 crossing, or current and also current should be 0. So that both condition is satisfied. So this thyristor will be off. This will be off at omega t equal to pi. Then the voltage is reversed. Input voltage is reversed. This is negative and this is positive. This thyristor is now forward biased. Now we have applied another pulse to T2. This will be IZ2. This will be IZ1. So if we apply the gate pulse with pi plus alpha, then we will get a symmetric output. You got my point?
Yes, sir.
So output for that I have plotted here. If I want to plot it here, so that will be your, so here, and then this is alpha, this is pi, and this is pi plus alpha, and this will be your twice pi. You got my point?
Yes, sir.
So what will be the average value? VDC. VDC will be integration of alpha to pi, then Vm sine of omega t, d of omega t, then divided by 1 by pi. Because this is repeating, we don't need to integrate both cycle. Only 1/2 cycle integration and divided by the time 0 to pi. That means pi. That will be your average value. You got my point?
Yes, sir.
If you don't say anything, then how can I know that you are understanding this?
Sir, I'm responding, but sir, am I audible, sir?
Yes, fully. So sometimes you can use the thyristor as a, this is the example of AC to AC converter. So like your regulator switch of your, at your home. So this is the track. Track is that the characteristics of the track will be like this. It will conduct both cycle, okay? Not only like the S here, it will only conduct in the positive cycle, but this thyristor, we look here back to back parallel diode symbols are here. So look here, If you apply a positive pulse, then it will be conducting one, it will be conducting from alpha. So we have given a positive pulse here, and also we also give another pulse here to this one. So this is your pi plus alpha. So then you will get the output voltage as this one. That means, okay, the average value will be 0, but the RMS value will be less than your Vs. You got my point?
Yes, sir.
This portion, this area will be deleted. So with this one, if you increase the value of alpha, suppose your alpha equal to 90 degree, then your what will be your wave shape of your output voltage? This one and this one. What will be the average if this is your 90 degree and this is your pi? What will be the average value? Pi plus 90 means 270 degree, and this is your 360 degree. Now, what will be the average value of this one? This will be your output voltage.
So we will have to segmentize it. I mean, one segment will be like the limit from pi by 2 to pi, and
no,
then
no,
another.
it is so your area A1 and this is your area A2. So area A1 equal to area A2.
Oh, so they will be cancelled, sir.
That means 0. Your average value will be 0, but your RMS value will be, you will lose this area. You got my point? You will lose this area. This area will be lost. That is why you are this way you are controlling the fan, the speed of the fan. You got my point? The speed is directly related to the RMS value. The speed of the fan, ceiling fan is related to the RMS value. So if you are just deleting this area and deleting this area, your average value will be same or it will be reduced. Sorry, RMS value will be same or it will be reduced.
It will be reduced.
It will be reduced, right? So if you reduce it, then your fan speed will be low, or if it is a light, say light dimmer, something like that, then it will be dim. The light will be dimmed. You got my point?
Yes, sir.
Hello. Okay. How many? Okay, now students 40. So slowly showing. Okay. So now equivalent dance floor model of the energy harvesting. So there are some modeling. They have given here to make you attracted on this thing. So if you have time, you can go and study some of the things. So, but for your exam, you don't need all these things. So here also it is mentioned that what is the ideal. I have already mentioned in your from the book of the Mohan, what should be the ideal characteristics of a switch. This is also given in this book, in the Harun al-Rashid book. You can, those who want to study from here, they can do that.
Sir.
So please, yes.
Sir, here it is mentioned, one word is mentioned like super device, sir. What is it, sir?
What is that?
Sir, in the last line, sir, the ideal characteristics of a super device.
Therefore, the characteristics of any real device can be compared and evaluated with reference to the ideal characteristics of a super device. Super device means, okay, suppose a diode, when it is on, practically, what will be the drop of the diode? What is this drop? Tell me.
0.7 volt.
0.7. Practically 0.7. Ideally?
0.
This is super device. You got my point?
Yes, sir.
Ideal.
So the ideal device.
Ideal device. Yeah, it should be ideal device.
Okay, sir.
Okay. Now, so you can have a look of this one and practice the practical device. And we have already told you, right, how the current will go, the voltage will be going down when if this is a switch. If this is a switch, we have already told you. We have given this figure from the Ned Mohan, right? When it works as a switch, ideal switch, then if it is turned on, the voltage should go to 0. The voltage, this is the VCC, the switch was off. So the voltage across the switch is VCC, But when it is turned on, it will go to 0 voltage. Actually, it should go to 0 voltage. We have shown in the Net Mohan book it has gone to 0 volt, but here they have shown a very little voltage. So then, and also the current should be 0 when the device is off, but it is not exactly 0 anyway. So the current will be build up, and then if we multiply this one and this one, we already got right a figure like this. Can you remember this one in the last class?
Yes, sir.
Hello. So here it is also given in this edition, 4th edition of this book, but in the previous edition they did not. But I think you should read from that Net Mohan, that it is okay. So I'm not going to details of this one. So now let us have a look from the table 1.3. This one of your Harun Rashid book. So diodes, there are 3 types of diode, 1, 2, and 3. So this is the power diodes. Power diodes means it will carry a voltage. It will withstand a voltage, reverse voltage of 400 volt, and when it is turned on, it can carry a current of 4500, that means 4.5 kiloamperes, and the switching frequency, that means you can turn it off and on by per second 1000 times, and switching time is 50 to 100 microsecond, and on-state resistance is 0.32 milliohms. So this is the general purpose diode, but we can buy some high-speed diode. So look here, the switching frequency is 20K, that means 20,000 times you can turn on and off per second. And switching time is also very low. And your on-state resistance is 0.4 milliohms. So I don't know whether you have heard the name of the Schottky diodes or not. Schottky diodes is unijunction type diode. That means P-type materials is sandwiched with the metal. So your breakdown voltage is low, but your speed can be increased here. So this is the Schottky diode. So please have a look from your any book of say Boylston or internet. You can have look up your Schottky diode. And then there are pot transistors. Pot transistors is bipolar junction transistor, BJT. So it could be single or it could be paired. In the Sidra Smith, if you remember that we have some circuit like this. Can you remember? Last topics of the chapter, we can make the combination like this. You can pair some. So these are known as the Darlington pairs. So this in a package, in a what I want to mean is that in a device, a Darlington pair means several transistors are paired, and that is available in the market. So the frequency of that one is say around 20K, and switch time is 30 microseconds. I am giving all these things not to memorize, just to have some idea. Okay.
Okay, sir.
So now there are some other devices like your, I should mention this one, like your MOSFETs, like your cool MOS. There is no new device known as the cool MOS. This is the insulated gate bipolar junction transistor, something like that. And there is this is static induction transistors. This one, okay. This one. Then your this is thyristor, phase control thyristor like this, what we have already discussed, and we can have a look. The voltage withstanding capacity has been increased, and also the switching frequency has been increased. So force turn off thyristor. There are some thyristor we can turn it off forcefully. Like I have shown the SCR, we see that it can be turned on, but the turn off can be only done when you have the voltage reverse of the current is 0. But you can some devices like force turn-off thyristor. And also, we have some more devices like your, so say RCT, reverse control thyristor, get light activated, get activated. I forgot that thing. Is that in the text it is given here? G2 is the get turn off thyristor. It is just like triad. We have already. So if you apply a positive pulse, it will be turn on, and if you apply a negative pulse, it will be turn off. So that is why it is known as the get turn off thyristor. Okay. So you just look at those things, have some ideas. So tracks is there. So track are the bidirectional. Bidirectional means go in the both directions the current can go. MCT is also bidirectional. MOS control transistor. So you can have this kind of devices also. So in your syllabus, it is mentioned that we can have some idea about the switches. These are the output characteristics of your the devices. Like this one is the diode, you know it. So this is your positive, and this is breakdown voltage. If you apply negative voltage, then after this one, there will be no current. But at this point, we call it, this is breakdown voltage, right? Can you remember the Zener breakdown I told you? Can you remember? Hello?
Yes, sir.
Okay. So this is a thyristor. Thyristor, if you apply a gate pulse here, then only the current will go here, and it will be turned on. And if you maintain a, if you have a latching current, they call it latching current. If you have a latching current like this, then thyristor will be turned on. But if you go back, the current is going to that, and there is another current known as the holding current. If you go beyond this holding current, then the thyristor will be turned on. And these are the three devices. Static induction thyristor. This is the get turn off thyristor. This is the MOS control thyristor. So it will conduct in the both directions, right? Okay, let me show the figure later. This one. These are the thing. See GTO. So the figure is not correct here. So it should be turned. You can turn off. Yeah. No, figure is okay. You can be turned off by applying. And look here. Can you see? Let me make it. Can you see the direction now?
Yes, sir.
Yes, you have, if you apply a positive pulse, it will be turned on. If you apply a negative pulse, then it will be turned on. So this is the gate turn on. And SIT has also the same thing. If you apply positive pulse, it will be turned on. And if you apply negative pulse, it will be turned on. So these are the devices that is available in the market. Okay. So you can have the idea of these devices output. Now, okay. Now that there are something that I must mention, the control characteristics of the devices. This is 1.9 of your book. So this is your control characteristics of the devices. Okay. Okay. So now, look, there are 9 types of characteristics it is mentioned here. First one is the there are some devices which are the characteristics of the uncontrolled turn on and uncontrolled turn on. Which falls under this category? You don't have any control to turn it on, and you don't have any control to turn it off. Your circuit voltage, the applied voltage will dictate you to turn it on and off. Which devices are falling under this category?
Diode.
diode. So in a diode, if you apply a positive voltage here, if this voltage is positive, then only it will be turned on, and when the voltage is negative, automatically the current is zero, and then this will be turned on. So that is why it is known as the uncontrolled turn off and uncontrolled turn on and uncontrolled turn off. But controlled turn on, uncontrolled turn off, which device should fall in this category?
Thyristor.
Thyristor. You can turn it on, but turn off will not depend on you. It will also depend on the voltage. If the current is zero and the voltage applied to this one and cathode voltage is reversed, then only the STR will be turned on. But there are some other devices that is controlled turn on and controlled turn off. That is BJT. If you apply the voltage, the BJT will be on. If you withdraw the voltage, the BJT will be off. If you apply the voltage, MOSFET will be on and it will be. And if you withdraw the voltage or reverse bias it, then it will be off. GTO, if you apply a positive, like positive current, it will be turned up. If you apply a negative current, it will be turned off. Sheath is like this. And continuous gate requirement means is that for the BJT, MOSFET, IGBT, and static induction transistors, one pulse is not enough to turn it on. You must, as long as you want that your transistor should be turned on, then you have to maintain this gate voltage, that means base voltage. If you withdraw this voltage, then the device will be turned off. So that is why it is known as continuous gate signal requirement. Pulse, only the pulse is enough to turn it on and off. This is SCR, GTO, or MOS control transistor. Bipolar withstanding capacity. So when you apply the SCR or GTO, it must withstand the voltage of the forward voltage as well as the reverse voltage. Why? In the forward voltage, unless you apply the gate pulse, it should not be turned on. And also in the reverse bias, it must not be breakdown. Ideally, it should not be broken down, even if you apply ideally infinite negative voltage. So that is why it is known as the bipolar withstanding capacity. But the BJT, MOSFET, GTO, IGBT, MCT, all these the devices are that it is only applied for the positive, either positive or the negative. For the for your NPN transistor, it should be positive. For the negative, for the PNP transistor, it must be negative. It should have the capability of the only unipolar voltage. Bidirectional connect. In track, I mentioned to you, the track will conduct in both the cycle, positive cycle and negative cycle. If it turn on in the positive cycle, then positive current will go. If it is turned on in the negative cycle, the negative current will go. Unidirectional current capability. This is the current will only flow through the diode and SCR, GTO, BJT in one direction. Okay, these are the things sometimes I set some quiz questions from this one. So these are important for your quiz question. Remember, quiz. So please try to understand and remember these things. Okay.
Sir.
Yes.
Are you giving your quiz in MCQ?
Yes, inshallah.
Oh, okay.
Inshallah. So you have the scope to communicate with each other, right?
Sir, how are you going to take the quiz, sir? Google Form?
Yes, Google Form. But the time will be very, very, very small, and there will be a lot of questions. So that you will not get enough time to communicate with each other, but even though you communicate.
But sir, please give us the standard time to answer, because sometimes it happens that there are too many questions, and like even without communication, we cannot control, we cannot actually complete the exam.
You cannot what?
Sir, suppose that there is, I'm giving an example, like suppose there are 10 questions and like I'm actually giving my exam and trying to complete the 10 questions, but sometimes the time becomes so small that it is not possible to,
then you have to give me the what that you will not communicate with each other.
No, sir, for MCQ, it's difficult to communicate with each other.
Right. But my experience is very bad, very bad. I am very upset with the last year, with the students of the last year. They communicate with each other. Anyway, forget it. I believe that you are good. You are a good boy and girl. Okay?
Yes, sir.
Okay, so now they have given you the thing that I have told you. Look here, you have applied a voltage here to the thyristor and you have given a pulse where? At the starting.
0.
Then if you give the pulse at the starting, just at omega t equal to, if it is omega t, and you have applied this one at omega t equal to 0, then what will happen to this voltage? That's just at the starting. You have applied the gate pulse. You have applied a positive voltage, say DC voltage, and you have applied a gate pulse at the beginning of the time counting. Then what will happen? From the beginning, it will be turned on, right? You understand it or not?
Yes, sir.
And then it will be your output voltage will be Vs. And if you apply a negative voltage on any other pulse, it does not matter. That the voltage will be always like this. I have already discussed this thing. You got my point? Yes or not?
Yes, sir.
This is your static induction thyristor and GTO. That means you can, if you apply a positive pulse, then it will be turned on, and you have applied a negative pulse, and this is off. So your current is 0, and you will get a 0 voltage. I hope you understand this one, right? Yes or not?
Yes, sir.
So these are some of the things you can have a look and understand the things nicely. Those who wants to do that. I'm going to next chapter. What is the time? How much time I have now? 20 minutes, right?
Sir, it is almost 9:55, sir.
Okay, that's good. So these are the characteristics of the diode. You know that this is the Shortley equation, right? Diode equation. Look here.
Yes, sir.
You are familiar with this equation already. So you don't need to do that again and again, because we have come this. Those who, this is the first course they have. Then this. So now I will give you some idea about the reverse recovery characteristics of diode. Okay. What is that? Reverse recovery. So are you familiar with the word reverse recovery?
Yes, sir. When we apply the reverse bias, that takes some time.
Right, exactly. So I'm repeating this figure, and I will use the my whiteboard. Okay.
Okay, sir.
Whiteboard now is in front of you. Can you see the whiteboard?
Yes, sir.
Suppose a diode, I'm not drawing the circuit rather than I am drawing the characteristic. Suppose this is your diode current. Your diode current, and this is your time t. So diode is on. So until this, it is on. So you have turned it off somehow. You have the circuit in Mohan and also the circuit that is I have shown you as a switch. So then you have turned it off. Then if you turn it off, then what will be the voltage? So when the diode is on, what should be the voltage across it?
So when the diode is on, so the source voltage.
It should be no. Across the diode. Across the diode. If it is on, then what is the voltage here? VA or VD. What should be the VD? If it is on, if the current flows this one, ideally, what should be the
ideally
voltage?
It is 0 voltage.
Right. And then when it will be off, then the voltage should be your VCC or the circuit voltage, right? You have to apply the Kirchhoff voltage to find out what will be the voltage. So then the voltage will be 0. And then when it is turned off, then the current will not go to 0 immediately like this. Rather than it takes some time and goes like this. Then current is 0 here, okay? But if it stops here, we will be very happy. But it does not stop here. Rather than it is going, and stop here. So this current will be known as the IRR, reverse recovery, peak value of the reverse recovery current. Okay. So now after that, practically what is going on? This current is going, and finally it goes to zero. Okay. So
Yes, sir.
this is the current, and now what people do. So when it is, the slope is negative and it goes to here. So this time is designated as TA. And okay, there is another line. So this is your, this one is the 25% of IRR. When the current goes back and it goes to the 25%, say if it is 100 ampere, if this current is 25 ampere, so then we count this one, and that will be marked as this one, and this will be TB. And this time, total time will be known as TRR, or that means reverse recovery time. TRR will be nothing but TA plus TB. So this TA time is required for the diode to sweep out the minority carriers across the junction. Suppose this is your PN junction. So there are some minority carriers here, maybe negative, and this is your minority carriers whole. So this needs to be recombined or vanishes. So it takes this time. When these are done, but there are some other minority carriers in, they call it inside the bulk of the semiconductor material. These also needs to be vanished. So it takes this time, this time. So altogether, this will be known as the reverse recovery time. This is reverse
Recovery time.
Recovery time. Reverse recovery means it has gone to reverse current, negative current, and it is recovered until this. If it is 25%, we are happy. Now we are ready to apply the next pulse to make your diode on. So during this time, it is the time for your diode to get recovered. So if you apply if you want to turn on the diode during this period, so it will not be turned on. Never. It will not be turned. You have to wait until this TRR time. Okay. So if this TRR that I have, when I was discussing about the diode, transistor, all these things, I told you that this is the switching time. Switching time means that it takes some time to turn off and it takes some time to turn on. So altogether, this is known as the switching time. So this is the nothing but the if this TRR is very, very large, that means diode takes long time to go to the zero current. So if this TRR is long, then your switching time will be less. You understand? You cannot turn on off very quickly. You have to wait maybe until this point to apply another pulse. So you have to wait we have to give a dead time to make the current to the 25% of the reverse recovery current, then only you are ready to turn it on. If this TRR is very high, that means your diode is slow. Your diode is slow. You got my point? What I said? Okay. Now we can drive some of the formulas that I am going to. Okay, there is another thing that is the TB by TA, that is known as the softness factor. What is this softness factor? So like what happened in some cases, in some cases, what happened? Just follow me. It has gone to here, but it is going to very quickly. So your TB, TA is larger than your TB. So if the softness factor is low, then that means it is going to very quickly to the reverse recovery characteristics is known as the abrupt recovery, quickly recovery. And this is known as the slow recovery. Okay, because TB is comparable to TA. If TA is much larger than TB, that means that is the abrupt recovery. Okay?
So then the abrupt recovery is actually good for us.
Yes, preferable. Abrupt recovery is preferable, definitely preferable.
So what
Now,
is the typical time of TRR?
it is mentioned in your data sheet. In your data sheet, it will be mentioned. It depends on the switching frequency, okay? So it depends. Sometimes it's a microsecond, sometimes it is millisecond. So normal general purpose diode has some say millisecond. But the first quick recovery diodes have them in the and maybe in the microsecond. Do you understand?
Yes, sir.
The range of the microsecond. Okay. Let me drive some of the equation now. So number one equation will be TRR will be your TA plus TB. So this is equation number 2.5. Now, if you know, do you know what is this one? This is the slope. How do you find out the slope? Because suppose you are counting the time 0 here, and this is your TA time. So what will be the, and this is the IRR. So we can write down IRR by TA is nothing but the di by dt. You got my point?
Yes, sir.
Y by x. Y by x, dy by dx. That means the slope of the current. Then from that one, we can write down IRR will be di by dt multiplied by TA. So that will be your 2.6. Okay, then now we want to find out the charge, reverse recovery charge. So we can say that this will be your say Q1, the charge accumulated during this triangle, that is say equal to Q1, and also the charge accumulated to this one, like the triangle, this will be Q2. So we can write down QRR, total charge. Charge is nothing but the current multiplied by time, right? So what is Q1? What is Q1?
Q1 is the integration of the total current in this time.
Right. That is the, so you have to find out the area, nothing else, right? So yes, we can write down this half IRR multiplied by TA plus half IRR multiplied by TB. So why we have not make the equal sign? Because look here, this we have taken the this triangle, and we have taken this triangle, whole triangle, but actually it should be only this time, this part. Okay, let me write this part, but we have taken this one. That is why we write down almost equal. So with this one, we can write down half IRR TA plus TB. So this is your equation 2.7. Okay?
Sir,
yes.
Is it not something following that minus e to the power minus x curve?
Yes, but we are assuming we don't want to make our life complex, rather than we take a straight line. Okay?
Yes, sir.
This is your TA plus TB will be TRR. So that is equation number 2.7. So now from there, then we can write down, from here, we can write down IRR will be 2QRR, which is almost equal to SAM divided by TRR. This is equation number 2.18. Okay? Okay?
Yes, sir.
Now, if you use 2.6 and 2.8, you can find out TRR multiplied by TA with your 2QRR divided by TA by TT. So equation number 2. Just hold on. Can you see now? 2.6 and 2.8. Where is the 2.8? Which one is
On
2.8?
the left side.
This one. Look
Yes,
here. This one. This one. So use these two equations, then you will get this one. This is 2.9. Okay. So until this you can use, no problem. But they have more approximated more. TR equal to TA plus TB. If your this one is much greater than this one, then can you write down TRR equal to TA? Suppose this is say 100 ampere and this is say 2 ampere. Can I neglect this 2 ampere? You got my point or not? Sorry, not ampere, microsecond.
Yes,
Suppose
sir.
this is 100 microsecond, this is your TB is equal to say 2 microsecond. So altogether 102. But can I write down this is 100? If it is 102 microsecond, can I write down 100? There will be not much error, right?
Yes, sir.
So if this, in any cases, if this happens, if TB is much greater than, sorry, TA is much greater than TB, that means very abrupt recovery, then you can replace this TA by TRR, then what happened? Where I have done. Okay. Then your TR, where is this? T. Where I have gone. Okay. Now, just let me go. No, I am sharing the whiteboard, right?
No, sir. You are sharing the book, sir.
I was sharing the book, no, this one. So now, if you place this way, so I have gone to the margin, you understand? That is why it is going like this. Okay, from here. So this is your TRR square, you will be your 2QRR di by dt. From there, you can find out. Let me erase this part and show you this one. So TRR will be your root over 2QRR divided by di by dt. So this is another equation you have, and this equation will be 2.10. And from there, you can also find out by if you replace this one with IRR, then we can also find out the equation of the IRR, that will be your 2QRR di by dt. This is very easy derivation. You don't need to worry about it. So, okay, we can use this equation. We can use this equation to find out TRR and IRR. But the condition is that, what is the condition?
So
what is that condition?
TA is much greater than TB.
Right. Suppose this TB, TA is equal to 5 microsecond. And if this is to say 3 microsecond, so can I say that TA is much greater than TB?
No, sir.
Maybe 10% we can allow, 10% of TA, right? Then you can use the formula. But if in any problem I say that, okay, take TA equal to 5 microsecond, TB equal to 3 microsecond, don't use this approximate formula. Rather than you use your geometry to find out the all the parameters. You got my point, what I say?
Yes, sir.
Now, I know how to go to the book. So at the end of this topics, there is an example.
Sir,
you
your
can see
book
that.
is not visible, sir. The whiteboard is
cannot,
visible.
You cannot see the book, right?
Oh, sir. So the whiteboard is visible.
Okay. Let me share the again. Now is it visible? Is it visible?
Yes, sir.
Book?
Yes, sir. Now it is visible.
Okay. Okay. So now look here, the reverse refinery time is TRR is equal to 3 microsecond, and di by dt has already given 30 ampere per microsecond. Per microsecond, it is falling by 30 ampere. And then determine QRR and also IRR. So you can use the formula directly. Okay, from equation, so you have this equation. Actually, TRR we got 2QRR divided by di by dt. This equation is 2.1. So with that one, we can write down this one, 2QRR divided by di by dt. So di by dt has been given 30, and also TRR has been given as 30 square. And from that one, you can find out the QRR, right?
Yes, sir.
So you can, and also you want to find out TRR, so you can use the formula directly. This one and find out 9. But if I mention that, okay, TA is equal to say 10 ampere, 10 microsecond, TB equal to say you take 5 microsecond. Don't use the formula directly, rather than you use the geometry and to find out this is your TA and this will be your TB. So this area may be given, this area may be given, use this area and you solve the problem. Okay. So I'll show you how to, I can make the question from here. If you go back to your previous year's question, of course you'll be able to see I have made the question this way so that you cannot use the formula. Those who use the formula, they will not get the full marks. So after the end of the chapter, there are 3 problems are given. Let me go to the chapter. Can you see that? Can you see it? Can you see it?
Yes, sir.
Hello. Oh. Already chapter 3 has, I have done to chapter 3. Okay. Time is finished, right? I'm very sorry that I took this time from you.
Sir.
Just wait. I did not take your attendance. Okay. At the end, there are some small questions are there. You can have to. So this is 2.1, 2.2, and also 2.3. These are the problems from that figure we have discussed. So please look at those and try to solve it. And if you cannot solve it, then of course I will help. But I'm very much sure that you'll be able to solve it. These are a very easy problem. 2.1, 2.2, and 2.3. Okay?
So, inshallah.
Inshallah. Good. So now I'm going back. Stop sharing. And then view option, gallery. I'm taking your attendance, okay? That's all.